Alright, hi everyone. Welcome to the start of our look into more detail in terms of the actual theory of the searching algorithms we're going to go through. Today I'm just going to get through um, kind of the early parts of the linear search. Should be more of just getting our rhythm going with the theory stuff, and we'll build as we go. So it starts off with just an overview. So it says the obvious: computers are tools which are used to solve problems for us. One of the things that computers are very useful for is storing vast amounts of data, and to make the best use of the machines, we want to have efficient ways of finding items in this set of data. And so we can look at the illustration at the top, and the reason this is kind of useful is that it demonstrates at least some of the notation that we're going to be using, or some of the terminology, not so much notation. So as you can see, position, also what I've been calling the index, is up at the top, and then at each index there is a particular value over there, right? And so the position is obviously ordered starting at 0 up to 10. Okay, so this will be n minus 1, where n is the number of elements. So in this case there are 11 elements, and so your last index is 10. Alright, again, I know it's easy when you look at it now, but when you're doing a proof, it's the kind of thing sometimes the -1 can trip you up and stuff. And then each of these are just the actual values, and those can be arbitrary. We're just going to keep them integers. So the kind of things you may consider with this kind of list is finding a position of the largest element, finding a specific element, or counting the number of elements with a particular value. For all these problems, they can kind of be adapted in ways that look similar to just searching for a digit. And so in this case, we're going to be focusing on just finding a particular value. We're going to call it the key, and we're going to assume that it may or may not appear in the list. Alright, so the key may not be in the list, but we are just going to assume that all of the numbers in the list are unique. Alright, so we're not going to have duplicates. All digits that are there, all values that are there, are going to appear only once. But it may not appear in the list, which is a slight generalization from what we saw in the lectures. Okay, and so in each of the sections, we're going to look at an algorithm and consider things like completeness, optimality, time, and space complexity, which we've introduced already. Alright, so we're going to get started with the linear search, so let's just describe it again for completion. So in our search, we start at the first element of the array and check it against the key. If it matches the key, then we have found the number that we're looking for, and we can terminate. If not, then the number that we're looking. If it's not the number we're looking for, then you move over to the next element and repeat, and you just keep carrying on doing this until you find the element. Alright, so if we're looking at this list here, we can start off at position 0, and you check if the value at position 0 matches the key. If not, then you're going to move this over to there, and you check if the value at position 1 matches, and if not, then you move it over again, check if the value at position 2, so on, and if key is 12, then we're going to move it over once more, and now see that at position 3, or index 3, you now have the value of 12. And so you can terminate, and you just return the index. Alright, so the thing you want to return is this up here. Okay, so you're searching for the value, but you return the index. Okay, so let's see the theorem as it stands. So theorem 1, algorithm 1, the linear search works correctly for any valid input. Okay, and so I've given you the algorithm here just so you can see it. So you start off at index 0 as we said, and you're going to just go into this while loop. It says while your index is less than or equal to n minus 1, and again minus 1 because this is the last index, okay, or last position in the list, in the array. And on top of that, my list is not equal to the key. Alright, so in the lecture we would have seen just this condition here, because we would have assumed that the value was in the list, right? So we didn't need that, because we didn't have to consider the fact that we may run over the edge. Okay, and so we just assumed that we would eventually at some point fail this condition, and so that was the only thing we need to track. But same kind of logic applies. If I haven't found the key that I'm looking for, and I haven't run past the last index, then I just keep iterating until I do. Eventually one of these two will fail, okay, and there's two cases. Either I found the key and that's why I terminated, or I ran over and that's why I terminated. And that's what this if statement says here. It essentially checks whether or not this was the reason or this was the reason. Okay, so this would be true for the next if statement, and then this would be false. Okay, so if index is now greater than n minus 1, so 1 more than that, then you just return minus 1. And this is just a placeholder, because obviously the index can't be minus 1 into the list, right? That is just a signal that it's almost like, a nan or something like that. It's just a reference to say that whatever we were looking for, that index doesn't exist. Okay? And then you return that index. So there's two cases here. Either this was the reason we terminated, in which case we went into this and we updated index to be minus 1, and so we'll return minus 1, or we found the key we were looking for, we don't go into here, and so then we end up just returning the index of the key. Alright, so how do we prove this? Well, we're going to do this by induction. Again, I think the important thing with some of these proofs that we're looking at, as much as they're simple, is to start understanding proof techniques and just building up our toolkit. And so as much as this instantiation of an induction proof is simple, it's practice in how we use the tool, which I think is what matters more. Okay, so induction starts off with the base case. Alright, and so we're going to start with n is equal to 1. So the simplest case, we have a list that is just length 1. Alright, so what happens if I have a list with a single element? Does this work? And so in this case, the base case is just tractable. Alright, and what we mean by tractable is I can manually reason through all possible traces through the algorithm. Alright, without it becoming a huge laborious task. And so that's actually just exactly what we're going to do. And this is a valid way of going about proving algorithms. You just trace everything. It's kind of like just setting up all possible test cases. If you pass all possible test cases, then your algorithm is true. Right? A lot of the times with these proofs, we don't have capacity to do that. We don't know how to do that. And so we have to find, kind of more mechanical ways or more, let's say, ways of grouping terms to try and do this. But in this case, we can just do it directly. Okay, so we're going to say the algorithm gets initially set to index 0. That's true regardless. And it gets checked in the first condition of the while loop in line 2. Alright, and so since index is 0 and n is equal to 1, the first part of the loop will return true. Okay, so is it less than n minus 1? Well, 1 is 1, so is it less than or equal to 0? It's set to 0 by default, and so that's true. Okay, second step is the is the value at index 0 equal to the key, and so we're going to have two cases. Alright, either this is true, and so you don't go into the loop, you don't increment, in which case you will fail the following if statement. Alright, you don't do that, and you just go straight to the return, which is index 0, okay, which would be correct. Okay, thus if the key is actually at that index, then it would return correctly. The second case is that the key is not at that index, and so in this case that will fail. That will be true, and so you will update your index once more. Alright, and so now you've gone from index 0 to index 1, and then when you go back over this loop now, you're going to say, is 1 less than or equal to 0? That is obviously false, and so now it will fail, and then you're going to move to here, and you're going to check this if statement over here, and it says, is 1 greater than 0? Alright, n minus 1 again at 0. That is true, and so you're going to update to minus 1. You're going to come down, you're going to return minus 1, which again is true, because there was only one index in the list, and by assumption, or by the setting for this case, it was not at this one index, and so saying that it's not in the list is just correct. Alright, and so you've set up a really, really simple initial test that amounts to no iterations, but just checking, can this algorithm handle whether or not it's in the list or not in the list by using that first index. Okay, then you're going to assume the algorithm works for a list of length n is equal to k minus 1, alright, and thus it returns the correct index if the number is present and minus 1 otherwise. Alright, and so you're just saying you assume k is greater than 1, and again the minus 1 here is just so that we can handle the edge cases, alright, and ultimately so that this case just becomes easier here when we set n is equal to k. Alright, so you just assume everything less than, accounting for the fact that it must be greater than 1, so that you don't get k is equal to 0 minus 1, which is minus 1. Obviously that doesn't make sense. So you just need to set up the values or the conditions on k sufficiently, but you just assume that k is something that sets this to be 0 or a larger number. And again, you can pick the notation. So in this case we do minus 1, just that we don't have to carry the minus or a plus when we move on to the actual inductive step. So we're just making this easy for ourselves in terms of the notation. One thing I do just want to mention in terms of this bit here, this is obviously mechanical, like once you've done the base case, you just then do the assumption that for everything greater than that, it's going to be true, and then you're going to go one step beyond that, that induction hypothesis. You could have done n is equal to 2 here. If you're wondering, like, why didn't we do that? You could have done n is equal to 2, and that proof would still hold. And a lot of times, using something as trivial as this is not a good idea. Right? It actually becomes a little bit harder because then you're not going to get code coverage and there's going to be exceptions and stuff like that, right? So one of the reasons we can set n is equal to 1 is I've still gone through all lines of code here. It's not like I end up in a case where I'm now missing kind of pathways through the code, and so I haven't sufficiently checked every aspect of this is correct. Alright, so you want to pick a base case that still sufficiently challenges the algorithm to check all of the possible paths through the code. Alright, and again, you can do this when it's tractable. Alright, so we do our induction hypothesis. Just assume that it's going to work for a large number of n, larger or equal to what the base case was. Alright, and you say, I assume it's going to work or return minus 1 otherwise. And then you do the inductive step. Alright, and so that's just literally taking whatever the size was for the induction hypothesis and adding 1 to it. And so in this case, it's now just k minus 1 plus 1 is equal to k. And so now you can try and prove the algorithm from here. So let's read this. So if the number appears in positions 0 through to k minus 2, alright, then it is within the sublist of length k minus 1. Alright, so it's within a length that we've assumed it can handle already. And again, because the 2 minus 2, it's because we're indexing from 0, right? So the length is k minus 1. The length up here was k minus 1, which means that the indices go from 0 to k minus 2. That's for this bit here. Alright, so again, keep your wits about you, whether or not you're speaking about length, which is 1 all the way up to 11 here, so you have 11 indices here, but the last index was 10, or the last position was 10. Same story. In this case, you have k items in your last index, k minus 1, or if you're doing with a list of length, k minus 1, so up to here. This is length k minus 1 over here, so this last index is k minus 2. Alright, so that's what's going on there. Alright, so we're saying that if the number appears in the first k minus 1 indices, then in that case it's going to be in index 0 to k minus 2, then is within a sublist of length k minus 1. In this case, the key will be found by the induction hypothesis, because having a new index off the end of your list does not change the problem. Alright, searching up to here when there is still this bit off the end, does not change our ability to search within this red region there. Okay, and so you can effectively then just ignore that, or say that your code will run the exact same way. All of the values for your iterator, all of the while loops, all of those I values are still going to be exactly the same. And so if the value is found in index 0 through to 9, it will return properly. Alright? By assumption, just by virtue of the induction hypothesis. Alright, and so in this case, the key will be found by the induction hypothesis. This means that the algorithm will return correctly. Thus, you only need to consider what happens if the number appears in position j is equal to k minus 1, the last index, or it's not in the array. Okay, so all we've done now is said, well, it's going to work for the first, all of them except for the last index. We just need to prove that it's going to work for the last index. And so to start, the algorithm sets index to 0, and we're just going to do this directly once more. You'll notice this actually looks a lot like how we did it the first time. Okay, it's very repetitive, just keeping track of variables now that are a little bit more larger and kind of getting to the end of the array rather than just being at 0 in a length 1 array. Okay, so if the list appears in position, sorry, I was wrong. To start the algorithm, set index to 0 and check the while loop condition on line 2, since we are considering the case where my list index is not equal to key for the first k minus 2 or first k minus 1 elements, so indices 0 to k minus 2. The while loop will enter k minus 2 times and increment index each time until index is k minus 1. Alright, so you're just reasoning through this part of the loop here. You set it to 0, and you just keep looping every single time, and you keep updating it until it's pointing to that last index. Okay, it's going to eventually be pointing to k minus 1. And so when index was equal to 0, you incremented that index to be 1, which is also why when you have index k minus 2, you'll enter the loop and increment to k minus 1. Okay, and so now when index is k minus 1, there are two cases. If the key is at that last index, then the second condition of the while loop will fail, right? Because the reason you halted over here is not because you ran past the edge again. By assumption, you've just set index is equal to this last index indices, so index is currently equal to n minus 1, and so this will still be true, and so the only thing that could have failed here is the fact that my list is equal to key, in which case when we come down to this condition, index is greater than n minus 1, that is false by assumption, because that first condition was true, or by the case we're considering, because that first condition is true, and so you're going to skip it, you're just going to return the index, which is now n minus 1, which is correct. Okay, so that's what this block is saying here. And then the second case is if my list is at the last index is not equal to the key. In that case, you're going to enter. In that case, you are going to have this being true and this being true. You're going to enter the while loop one more time, and you're going to add +1. In which case, your index is now n. Alright, so index is going to get set to n. Is index less than or equal to n minus 1? Which is obviously not if it's equal to n. So that'll now fail. And you come to this if statement, it says is index, so n greater than n minus 1. That's true. And so you're going to update it to -1 and return the -1. And so once again, you've kind of just gone through the process and manually shown that all the paths through the algorithm are covered, and that either it will find the index at the last element of the array and it will return correctly, or it will not find it and it will return -1. Okay, and so your conclusion is by induction, the algorithm works correctly for lists of all lengths. Alright, and so you're probably wondering, well, it feels like we left a big gap in the middle there, but if you are uncomfortable with this induction hypothesis, then all you have to do is set this k minus 1 to 3. Right, and so all that's going to happen then is n is going to be equal to 2, which is 1 further than, sorry, my bad, you need to set k is equal to 2, k is equal to 2, in which case n will be 1, which is exactly what we've just proven above here. Okay, and then the one step further, we'll now have n is equal to 2, and we've just shown that when n is equal to 2, or any increment further, you now have, it will work, right? So by assumption then, it didn't return true in the base case. We've shown that directly that it will if it was in index 0, and so all we have to now consider is that 1n further when n is now equal to 2. Okay, and we just proved that as well. The benefit we get from using arbitrary indices, though, is that your question may come in, you may say, well, okay, you've shown it for n is equal to 1 and 2, 1 or 3, 1 or 4, 1 or 5. And so what you do is you put the symbols on it, right? You assume it works for everything up to the index you're going to challenge me with, and then I'm just going to prove it to you that the challenge works. But because it's left general, what you're effectively doing is covering the case where you say n is equal to 1, proved with the base case, n is equal to 2, proved with an inductive, or proved directly for the next step, n is equal to 3. Well, you've proved n is 1 and 2, so we can take those for granted, and you're going to prove n is equal to 3 again, and next time, and so on. So there's almost like an implicit for loop in your proof when you're doing the induction hypothesis or induction technique. Okay, so that's that proof. I hope that's fairly old hat, but we can go through it more if there's problems. Okay, then we can consider the optimality of the algorithm. I'm trying to remember, is this where I wanted to stop this for today? I do not think so. No. I know where to stop. Okay, let's consider the optimality of this algorithm. So, algorithm 1, linear search is optimal for unordered arrays. So the proof in this case, we're going to say, in order to determine whether an algorithm is optimal, we first have to establish a lower bound on the number of operations needed to solve the problem. Because remember, the definition of optimal is that our algorithm, in the worst case, never does more work than we need. Okay, so we need to show that the worst case complexity of our algorithm is equal to that lower bound of needed to solve the problem. Okay, and so the problem that we're dealing with here is to determine the position of a number in a list of numbers or an array of numbers by doing comparisons of key. Alright, it's the number we're looking for with numbers in various positions in the array. We need to find a lower bound on the number of such comparisons, which must be done by an algorithm to be guaranteed to solve this problem in their individual worst case. Alright, and so it's an individual worst case for each algorithm. Okay. And so remember that we do not know anything about the order of the values in this right now, and so you can just prove it by contradiction. So one thing to note here, what we're going to see in this proof now, is that I've showed you an algorithm where you initialize to 0, and then you hop and you look at 1, and you hop and you look at 2 and 3 and 4 and 5 and 6 and 7. Now that's a really intuitive way of going about it, but there could be another algorithm that starts at the end here, and it hops to the left. Or you could arbitrarily do any sort of ordering. You can do something that looks quite random in how it jumps around, and as long as it's checking each index once, it's fine, right? That is a valid search scheme. And what could be interesting though is if you have this kind of search scheme which starts at 6, and let's say the key was 45, you're going to find that in one step. But if you have another algorithm that starts at 9 and then goes through a whole big sequence, let's do this, and only at the end jumps to 6, well, now that's going to find it at the last point, right? And so you can do this arbitrary search through the indices, but any algorithm could pick a different ordering of indices. And because they're all just quite, the ordering is numerically meaningful, but the search order means nothing. We can't do a proof and say, oh, that algorithm 1 was optimal because it was found in one step, right? That's not the case. It's each algorithm's worst case. So if we have algorithm 1 that's doing, this loop here, I'm just going to jump around randomly. Okay, then we're considering how many steps it had to do to get to 10. If I have another algorithm jumping around at the bottom here like this, let's do that, then its worst case would be to get to 7. Okay, and that's what I mean, my bad, I missed the 4. And so this is what I mean by we have to consider each algorithm in its individual worst case. The blue algorithm's worst case is index 7. The red algorithm's worst case is index 10. And so we have to consider the lower bound amount of work that any such algorithm would be doing in each of their individual worst cases. And so you can see that in an arbitrary ordering, there's going to be some index that comes last, and they're going to have to search through all other indices first. Okay? And that's the whole crux of this proof that we're going to show now, and we're going to do it by contradiction, alright, which is another proof technique you can have in your belt. But this is the kind of idea here, is all we're going to do is assume that what I just showed you is not true, and we're going to contradict that fact. Okay, so any search algorithm will need to check one index at a time until it has checked all n indices. That's the first step. Alright, if they can check multiple indices, if there's some quantum version of this, then this doesn't hold anymore. Alright, so you have to check one at a time. And so assume that an algorithm exists which can find the key or determine that it is not in the array assume that an algorithm exists which can find the key or determine that it is not in the array in less than n comparisons. So assume there is some algorithm that's guaranteed in its worst case to not have to check all indices to get to its last index. And you can really see that linguistically or verbally that's starting to not make sense, right? I just said to you it doesn't have to check all indices to get to its last index, but then that wouldn't be its last index if it hasn't checked all the others. Alright, and because it has to do them in sequence up at the top here. Alright, you can see the logical steps flowing, and again, this is rigor. It sounds silly saying that, but that's the kind of, you're getting all of the machinery set up early on up top here, so that you can make really clear claims. Okay, so consider the algorithm performing k comparisons, alright, and that's n-1 comparisons, so one less than the number of items in the array. And we're going to find the indices that the array checks in order. Alright, so it's their own individual order. So S1 up to Sn minus 1. Okay, and so again, S1 may be 6, S2, my bad, S2 may be 0, and so on. So this is symbols representing each algorithm's individual choice of indice ordering. Okay, and so for example, the algorithm begins by checking at index S1 for the key, and so it says my list S1 is equal to key, and so it's just going to keep checking S1, S2, S3 until it finds the key. And then you're going to let Sn be the index which the algorithm does not check. Okay, because again, by definition, if it's checking all of the indices one at a time, there are n indices, and you assume it doesn't have to check all n, then it means that there's going to be at least one. In this case, we've just said, for the sake of the proof, that there's going to be this one that it doesn't have to check. Okay, and so we can then construct an input list where you put the key in the one index it's not going to look. Alright, you go and you hide the key in the one blind spot of this algorithm. And since the values in the array are unique, then you know that it's not going to find it somewhere else. Alright, and so I just put a note there. Note how we have left the indices to be general. This ensures that any such algorithm's worst case is valid. We just hide the key in the place it won't look in the last place. It will look wherever that may be. So it's specific to the algorithm. Sn is general. Whatever algorithm we want, whatever search order, I can just stick it in the one index it's going to not look at until the very end. But in this case, the algorithm reached the end of its n-1 indices. Alright, and again, it's only ever going to check n-1. It's going to reach the end of its n-1 indices and not know where the key is in Sn or not in the list. And so in this case, it doesn't know whether to return Sn or return -1. Thus, to return correctly, the algorithm will need to check whether or not Sn is in the key, so it can disambiguate these last two conditions, which contradicts our assumption that it doesn't have to check all n keys. It can do n-1. This is a new, unique key check that we assumed it didn't have to do, which just contradicts us. Therefore, there is no algorithm which is guaranteed to produce the correct output for any input array of length n in less than n comparisons. Alright, again, in its worst case. And so this just follows by the kind of proof technique. So what you do is you start with an assumption. Here it is. So you're going to assume that an algorithm exists that can find the key or determine that it's not in the array in less than n comparisons. And once you get to a contradiction, you just state the opposite of that. Alright, in which case that is not true. So there is no algorithm which is guaranteed to produce the correct output given either finding the correct index or returning -1. And so in this case, now we have to actually finish the proof, right? And again, we have to go back to the definition of optimality, which also says, well, is the algorithm complete, all right? Which we just, or correct, either way, in which case we've just proved that, right? It is correct, it is complete. So it will return the right value. And so that's step one of that definition. And again, if I'm asking you this in a test and something, I am checking that we can be rigorous. All right, I want to see that we remember that optimality requires completeness first. And then the second condition, it takes at most n, a linear search takes at most n comparisons to return the correct output for any input, which matches the lower bound on the algorithm's worst case. So in this case, Sn will be equal to n for the linear search, but it could be anywhere else for any other algorithm, and all of their worst cases are going to do n comparisons. And so it is optimal because now it uses the minimum number of necessary comparisons in its worst case compared to any other algorithm and for the problem in general. Thus, the linear search performs the minimum amount of computations necessary to guarantee that the correct solution is returned in its worst case. Alright, therefore it's optimal. So you want to finish off properly. Finish with the clear statements, restate the definition at the end, conclude properly. Okay, so there we go. We have two proof techniques. We just covered induction. Alright, so learn the pattern. Start with some kind of easy to work with base case. You want to have good code coverage still from that base case. Then you're going to just generalize to arbitrary indices or arbitrary size. And then you're going to prove it for one more scale beyond that, where it is very easy then to use this assumption once you've either eliminated one option or, as in this case, to get to the last option. Alright, so that's the strategy there. It's when you want to assume away something like a loop. Alright, or it's a case where once I've done one step, it's going to look back like an old problem, in which case I can then just inherit the solution to that. So it goes both ways. Proof by contradiction, again, you just want to find one case that isn't true, or in this case, you can't just kind of, you can sometimes say a contradiction if you say, like, this algorithm is correct, or you just show an example where it's wrong. In this case, we need to be a little bit more general because we're dealing with all algorithms. Alright, we're not just saying it's one sequence of S1 through Sn minus 1 that's going to be wrong. We're saying all algorithms cannot perform less than n operations. And so we just have to be general about those indices. But that's the only thing we have to generalize to, is all algorithms. And in this case, for searching through a list, all algorithms, the difference between them is just defined by the sequence of S1 through Sn. Okay? But it's the same exact thing. If I gave you a specific sequence of S's, right, so I just said it's 1, 4, 3, 6, and the last index was 0, but I told you this algorithm, call it, S star, I said that actually it's unnecessary for S star to ever do n comparisons, then I've been specific. I've been specific in my theorem about the one algorithm, in which case your contradiction is to say, Devin, I'm just going to hide the key in index 0. Okay? We unfortunately don't want to be specific just to S star, so I have to then leave it general, in which case I'm going to use a symbol instead, Sn. And so now I've contradicted all possible algorithms at once. Okay, that's the only thing that's happened here. But if I gave you a specific algorithm with a specific search sequence and I said it doesn't have to ever check that last index, you could still do the exact same thing. You could still go and hide the key in that last index, and there you wouldn't need to be general because you just want to contradict one algorithm. But I currently want to contradict all of them. But that same intuition should hold. Alright, I'm cognizant of time. I don't want this to go much longer than it has to, since it's only meant to be a 45-minute tutorial. I'm going to try and get through the time complexity quickly for these algorithms because I want to spend time on the average case next week, and I want to make sure we have time for that. So we're going to do the complexity quickly. So to perform analysis of the time complexity, we must decide on what we define as a unit of work. This is not a trivial decision, as we aim to find a unit of work which is representative of the actual algorithm and the work done by the algorithm, but it is not as complicated. Alright, so you calculate the actual amount of work would require us to measure the physical computations on the transistors or something similarly complex. So we want an abstracted unit of work, but it's one that's still representative. And so in this case, we're going to work with the number of comparisons conducted on line 2 as our abstract representation, as it seems reasonable because this is where most of the decisions are happening in the algorithm. Okay. So what is the best case? So what we do here is we consider the best case, alright, and we decide on what we're going to set to be our functional form of the complexity, and then we prove it, right? I think a lot of times in the past you would have just seen something like this and stopped. In this course, again, I want us to go and prove it at the end. And it's really easy. I mean, I know that that's just straight. I know you can do that. Again, we practiced that in the first tutorial. But again, I want us to remember that this is the rigorous step. This is the problem solving. This is us understanding the problem. This is the proof that follows. Alright, and I know the proof is easy once you understand the problem. Cool, so in the best case, you would only need to check the condition on line 2 once. So just to remind us, line 2 that we're counting here is this while loop. Alright, where we check whether or not we've looped out of the index or found our key. So it's the comparison step to see if key and index, if the value at the index is the key. So in the best case, you are going to find it immediately. Alright, in this case, where you only need to check line 2 once. Okay, in this case, index will be initialized to 0 regardless of the input array. And so the index is going to be less than or equal to n minus 1 for all arrays, so we don't need to care about that. But then, in this case, is it going to be my list index equal to not true? That'll be false, because we only want to check it once, and that's the only way we can actually evaluate the full loop to break out and be false. And so we're now going to have to set that equal to key. Okay, so the algorithm tells us how to break out of that loop quickly, right? We just went and looked at it and said, well, I can't do anything there. That's going to be true by default given the initialization of the algorithm, and that's fixed. So the only flexibility I have is to decide on index and key so that this evaluates once. So how do I get it to be immediately false? I make sure that this is equals. Okay, so that's the method. You just go and reason through that algorithm, keeping track of the fact that our only free variables here in the problem setup is index and key. Alright, well actually not even index, it's just where we stick the key. Index is initialized to 0. And thus the best case is when the key, so the only flexibility we have, the key is at index 0 and the number of comparisons is 1. Okay, and we want this to be general to the input scale, right, when we're doing complexity analysis. Alright, so we can't go and manipulate n like that. We can only manipulate properties of my list, which is the other argument to that function. Alright, we want n to be left general by virtue of it being a complexity analysis. Okay, that's the best case is when the key is at index 0 and the number of comparisons then is 1, in which case g of n, the functional form, is equal to 1. Alright, where g of n denotes the unit of work. I will acknowledge that in the first set of slides I used f instead of g in this case. I need to consolidate these at some point. G is just way easier to do in these notes. Okay, so now that we've calculated the amount of work in the best case, let's actually prove its time complexity. This was just the calculation for us to understand the problem. We're now going to prove it. And so we have theorem 3 saying that algorithm 1 is order 1 in the best case. And then we go and take our general definition, right? The general definition for g of n being big O, h of n, where h of n is our complexity that we think it is in, is the following. So g of n is going to be less than some positive real constant times by the functional form we think g of n is bounded by for all sufficiently large n. And again, we can just pick the values, right? We have this. So we have that, so we can just pick n0 and we can pick c. By the definition, those are free variables, those are parameters. As long as it's true then for all n greater than that. So we're just going to pick, we're going to say that g of n is equal to 1. That comes from the, g of n comes from our problem we just solved up here. So that gets substituted in there. H of n, that just comes from the complexity class we're putting it into and testing. Obviously, you could do a similar thing with n and squared and so on, and you would still get big O being correct. You would get little o not being correct, but we aren't going to do that now. Alright, and so then all that's left, once you've substituted in g of n and h of n, and I would do this step first and then reason about it, is just to think, I now have 1 is less than or equal to c times 1 for all n greater than or equal to n0. Alright, and c is elements of the positive reals. So I just have to pick c and n0. Well, if c is equal to 1, then this whole thing just still evaluates to 1. So I haven't contradicted anything there. That's fine. And then you can see that there's actually no n0 over here. And so I can actually just leave this general. So it's for any n0 that's an integer in this case. Okay. And so we can just pick and say it's going to be fine for a is equal to 1 and n0 is equal to 1. And then you substitute all of that in and you check that it holds true. And indeed, it does just hold true everywhere. Therefore, algorithm 1 is order 1 in the best case. Alright, so again, this is just a direct proof. You've just started with a definition, substituted in your requirements, picked the free values that you have, and checked for consistency. If consistency holds, then it's proved. Let's do the worst case. So in the worst case, you would need to check the condition on line 2 repeatedly until you run to the end of the array. Okay, in this case, until the n minus 1 is less than false, so that you run past it. In this case, index will be initialized to 0 regardless of the input array, and so index less than n minus 1 will be true at the start regardless. But now we're going to pick my list index equal to key will need to be true every time so that we keep looping. Alright, so again, in that unit of work line that we cared about, we had one little bit of flexibility where we stick key. So in the worst case is when index is incremented by 1 from 0 all the way up to n, right, where n is now out of bounds because our last index is n minus 1. This will take n comparisons on line 2 where the key is not at index every time, and so for a list of length n, this would mean that the key is not in the array, which results in the n comparisons we care about. Alright, so you're just going to loop over and over and over until you've gone out of the list. Okay, instead, now that we have calculated the amount of work in the worst case, let's prove the time complexity for this worst case. Same story, you bring in the definition of big O notation. Now we're going to say, well, I calculate the amount of work to be n, so that's what gets substituted in for g. Here is the complexity that I think that is in, the big O, the functional form of big O that I think it's in. Substitute that in. Again, you do that in one step, and then you pick your values. And once again, this works. If I substitute n in here, I can then just set c quite arbitrarily, and so it will be anything greater than 1. So I just set, I said a there. I need to fix this. This is meant to be c. My apologies. Did I do that up here or did I fix it? Yeah, it's meant to be c up here as well. Alright, I will check that. Sorry for the inconsistent notation there. So you just pick your c, your constant out front, you pick n0 equal to 1, and again you check that it holds true. Therefore, it's big O, n in the worst case. So again, in terms of proof technique, you just took your definition, slotted it in, and checked for consistency. Alright, so I think that's where we're going to leave off today. We'll do the average case complexity next week. You can see it's a little bit of a long thing, but I promise you it's actually not too difficult. We will cover it nice and slow, and we'll get through it. All right, thanks everyone.